Hi, I'm Sandra Porter, and I'm going to talk today about using Protein Blast and IC in 3D for drug discovery. So we're going to start out by going to the NCBI and selecting Blast. There are multiple kinds of Blast algorithms, but today we want to look at the one where we can take a protein sequence and compare it to a protein database, and that is Protein Blast. There's some other alternatives here. You could see if you had a nucleotide sequence, you could compare it to a nucleotide database. You could translate a nucleotide sequence and then compare it to a protein database. Or you could take a protein sequence and compare it to a case where the whole database is translated. But we have a protein sequence, so we're gonna compare it to a protein database, so we use Protein Blast. Okay. So what I'm going to do here is I'm going to enter the accession number from a protein sequence where I have the structure, and the structure contains a drug that is bound to the SARS-CoV-2 protease. All right, my accession number consists of the 4-letter PDB ID followed by an underscore. Oops. Followed by the letter that designates the chain that contains that protein sequence. Okay, the next thing I'm going to do is I'm going to select the database that contains protein sequences from 3D molecular structures. And that database is the Protein Data Bank Proteins, or PDB. So it contains sequences from structures. Okay, the other thing I'm going to do, which I already did, but we'll do it again, is I'm going to pick sequences I'd like to exclude from my results. And I'm doing this because what I want to know is I want to know about potential drug molecules that might be in protease sequences that are related to SARS-CoV-2 but are not SARS-CoV-2. I'd like to see things that other people have studied, because I think this might be more informative. So I'm going to enter SARS-CoV-2 here. And when I see it, I select it from the list, and then I'm going to click exclude. So those sequences are not going to be part of my database search. And then I'm going to check the algorithm, which I see as BLAST-P. I might look at the parameters. And in this case, I have a word size of 3, which is going to be a little bit more sensitive search. I could even make it smaller, but I think 3 is going to be okay for our purposes right now. And I can close this and we will say BLAST. Okay, this can take a few minutes, but I already did the Julia Child thing and my results are here. Okay, and I can see I've found 58 sequences from my BLAST search. And let's go through the results. So here is the sequence that I entered here. Here is the request ID. And you can see it says that the search expires November 18th. So what this means is that if I wanted to look at my sequence tomorrow, I could do this. I would have to make an NCBI account, but I could log back in and I could see my results. Okay, I can also see the program that was used, the database that I searched, the description of the sequence that I used, since it's a sequence that's in the database. I can see that this is an amino acid sequence that was 306 amino acids long. And there's a little bit more information I can get as well. I can also look here where it says search summary. And this tells me other information about my search. It tells me the word size. It tells me the matrix that was used. It tells me the window size, the threshold. Also, one thing I find interesting is it tells me the size of the database that I searched. And you can see here, number of sequences. I searched I didn't search, BLAST searched 132,275 sequences, and it found 58. It also shows me the length of those sequences altogether, which are 35 million, over 35 million amino acids in those sequences. So it searched through all that information pretty quick and found 58 that match pretty well, which we'll look at in just a minute. Okay, so what else do I see in my search? I have a whole table of descriptions we'll come back to in just a moment. I have a graphic summary, and what this shows me is it kind of shows me, here's my query sequence, all 306 amino acids, and the red lines show me that the BLAST scores are all over 200 for all of these, so that's a pretty good match. And it shows me kind of the length of the matching sequence. So you can see here, most of the sequences that we found in our database search are pretty close to the same length as my query. There's a couple here though that are shorter. Okay. All right, so that's some information. I can also look at the taxonomy here, and I can see how these sequences grew. I can see that a lot of them are coming from SARS, which makes sense. It's pretty closely related. There's some from MERS. MERS is the Middle East Respiratory Syndrome coronavirus. There's 12 here from a bat coronavirus, 3 from a mouse hepatitis virus, 4 from a human coronavirus, HKU1, one of the causes of the common cold. I've got 12 here from a pig epidemic diarrhea virus. I've got 1 from a cat feline infectious peritonitis virus. And it looks like actually I've got a few more, 4 more down here from the feline infectious peritonitis virus, and a few more from the pig virus too. Another transmissible gastroenteritis virus, and then a couple more human coronaviruses, NL63 and 229E. And then I've also got infectious bronchitis. Okay, so that kind of gives me an idea what I'm going to find in my descriptions. Now let's look at the descriptions here. And I can see here, if I go to the descriptions, that I've got this whole big table of data. And now we don't actually need all the data. And so we're going to get rid of some of the columns so that it'll make it easier to read some of the other information. So what I'm going to do is I'm going to get rid of the scientific name. I'm going to get rid of the accession length. And I'm going to get rid of the total score because I'm not really going to need that here. Okay, that's pretty good. And that makes it easier for us to read. Oops. Let's try that again. Actually, we'll get rid of the max score. We'll keep the total score. And we'll get rid of the accession length. There we go. Now I can read some of the complete descriptions a little bit easier. Okay, so we have 58 sequences here. We can look at the information about these sequences. First of all, we have the total score, and this is a score that's assigned by BLAST to indicate the number of amino acids that match between the 2 sequences and how well they match, and the probability of matching. We also have a value here. It says query cover. And actually, I think we'll get rid of that too. That is telling us about how long the match is between our sequence and the database sequence. And we already looked at some of that information in the graphic summary. The BLAST score will kind of give us an idea about that as well. We have here some information, the Evalue. information. And this is interesting because, in fact, let me sort this. I should be able to click and sort. There we go. So what the e-value represents, so if we scroll down, we can see that the e-value goes from something close to 0 to 6 times 10 to the negative 73rd. All right, so what is the e-value? Well, the e-value tells us the number of matches that we could expect to find that match equally well as whatever sequence we're looking at here to our query sequence in a database of equal size that would consist of random sequences. So in a way, the e-value corresponds to the probability of finding a match that's random. And if we've got a probability that's 6 times 10 to the negative 73rd, that's pretty low, all right? In other words, those sequences are very likely to have evolved from a common ancestor. And these matches, it's not actually 0, but it's so close to 0 that we can't print it on a web page. The number in the exponent would just be too large. So they round it off and show you a 0 instead. In other words, there's just no possibility that these sequences are matching randomly. It's that low. Also, in this column here, we have the percent identity that shows us the number of amino acids that are identical between the two sequences that we're comparing. And last, we have the accession number. And the accession number is kind of like you might think of it as a catalog number. It's a number that we could use to find our sequence in the database. Okay, so let's take a look at these descriptions here. We are looking for protein structures where that matching sequence is bound to some kind of inhibitor. Inhibitors are molecules that could possibly be drugs or used as drugs if they're developed and studied and maybe modified. So inhibitor is a word that we could use to search with. I can use my keyboard command, Command F or Control F, and I can type the word inhibitor. And you can see here it's kind of small, but you can see there's 18 of these sequences contain the word inhibitor. So these are sequences that I might look at if I'm doing drug discovery and I want to find something interesting. Other words that tell me that there might be a drug in my structure would be bound. So you can see here, X-ray structure of FIPV3CL pro bound to a covalent inhibitor. That tells me that there is an inhibitor bound to something. Here we've got covalently bound. All right, another thing that might be interesting. Another word, and you can see there's 5 structures that contain the word bound. Another word that indicates that there might be something bound to our protein is with. So here we have the human coronavirus 229E CL3 protease with whatever this EPDTC is, some kind of inhibitor probably. And you can see here there's a substrate with NEMO 231 with whatever this chemical is. And those might be chemicals that people have been researching to see if they could be potential drugs. So 3 words we can use, and there's probably more, that would tell us if a structure might contain something we're interested in. And I'm going to sort these again by clicking the e-value. The other thing to know is that these structures are all grouped by the match between my query sequence and the sequence in the database. And what that can mean is that sometimes there can be structures in here that contain a drug, but I do not see that information in my description. So for example, if I look at, I think I'll look at this one. Yeah, that's an example. That's a good example. Okay, So this one, in my description, I only saw one sequence. Let's go back to descriptions for a minute. I only saw one sequence, crystal structures of SARS coronavirus main peptidase inhibited by azapeptide epoxide. Okay, but when I click this, that takes me to the alignment section, and you see it says see 3 more titles. Let's take a look at those 3 more titles. Okay, so these 3 more titles, one of them has the same azapeptide epoxide, but the other has something a little bit different. Like this has an additional alanine at the end terminus of the protomer and a different space group. And this one has something different too. The reason they're all grouped together is that the protein sequences are identical, but other components of the structure, like drugs, inhibitors, other things, can be different. So if we're doing drug discovery and we're trying to be careful and look at everything, we would be careful about looking at our alignment data and look for these other things where we have additional titles, and we might have additional molecules that we would want to investigate. Today, though, we're not going to look at everything. But if we were working in a company and we were doing drug discovery, we would want to look at everything we could. Okay, so I'm going to go back to descriptions here. I'm going to pick something at the very bottom, and we'll take a look at this infectious bronchitis virus protease. We'll use this one as an example. Okay, so I'm selecting this, and before I forget, actually, I'm going to talk a little bit about alignments for just one moment. So if I go back to descriptions, I go all the way back up to descriptions, or even close, but I don't have to go all the way. I want to point out something about the alignments here. So each alignment has the query sequence that I used on the top, the subject sequence from the database. In this case, the subject sequence would have been chain A3C like proteinase from SARS. And in the middle is information about whether or not the amino acids between the 2 sequences match. So if the sequences are identical, if the amino acids are identical, you see them appearing in the middle. If they're not identical and they're not similar to each other, there's an empty space like I have right here. If the 2 amino acids are similar to each other, we would say that they're conserved. They have same chemical properties, same shape, similar structure. There's a plus that shows they're conserved. That information is all reflected in this top information up here. So here we see identities. That tells me 293 of the amino acids out of 306 are identical, or this is 96% identical. Positives is telling me about the identical amino acids and the conserved amino acids. And that says 301 out of 306 are similar, and that for positives, I have 98%. And there aren't really any significant gaps where I don't have matching sequences. Okay, going back to my sequence that I was looking at before from infectious bronchitis virus, I can see here that 129 amino acids are identical out of 316. Should be 306. Anyway, 129 are identical for 41%. And 55% of those amino acids are conserved. Oh, I see. It's giving us 316 because we've got a gap, big gap here, where there are amino acid sequences in one protein, but not in the other. That's why it gave it 316. And it looks like we have 19 gaps. So like, here's a gap. Here's a gap where we don't have anything matching. Here's a gap. And so on. Here would be a gap. So any spots where we've got a larger number of spots where the amino acids just don't match each other. Okay, and I could see here I've got 4 more structures that are identical. This one does not contain any kind of inhibitor. All right, there's nothing to indicate that it does, but these two do. So I'm going to look at one of these structures. And before I do that, I'm going to copy this information just by dragging my cursor across it. And I'm going to paste it into either a Word document or a Google document. So that I can work with it a little bit later. Now I'm going to select everything. And I'm going to change the font to 10 so that I can see everything all aligned like I see it. So all the amino acids are lined up the way they should be. Okay, and we'll characterize the protein in a next video. Thanks.